waterfall. Well, there's all sorts of shit on so we're going to talk about inner product today. Wrap that up. Wednesday, swear, no matter what else happens, it's going to be skill check day. We're just doing it, no matter what happens or doesn't happen today. We'll, oh, that's right, I learned this lesson last time. Does anybody have anything they want to ask about before we do this? Any clarifications? Stuffs? No? Good? Okay, cool. How's everybody doing?
Stellar.
What's up?
Stellar.
Stellar. Outstanding. Outstanding. Very good. All right, let's get rolling. Seems very serious and attentive, so I better get moving here. Look, Jackie made me a mug cozy. Isn't that nice? Very nice, very lovely. All right, cool. Let's talk about inner product. What does our book call it? Dot product or inner product? Dot product. But it's also inner product, so I might slip. Inner product, I think, is a grad level word for dot product. It's kind of a more general thing. Hey, hey, hi. Oh yeah, yeah. I thought I took your seat. What's up?
Sorry,
Let me get that stuff out of you. Go, no, go, sorry. Sorry, I was just trying to clear space for you.
I should have to see.
You doing? Yeah, you're welcome. You got front row today.
Oh, yeah, I'm lucky.
That's one way to look at it. All right. Seems so crowded here today. It's crazy. And it's not just the one more. There's something going on. Anyway, so the dot product. So this is something we can define in any space that's a linear space, for the most part. An inner product is kind of a way to measure angles between vectors, but a vector can be all sorts of things. A vector for us is going to be something in n-dimensional space, but it could be something in infinite dimensional space. It could be a function. A function is actually a very fancy vector. We're not going to get into how or why, but this inner product, you can think of this as we have a strong geometry that allows for angles to be measured. And angles could end up being like a weird thing, like what the hell is the angle between x squared and x cubed? I don't know, but we could define it, angles between vectors. And this pen just blows so bad. Let's see what we got here. Now we're better. Is that visible even? Corners of the room, we're good. Cool. Do we need to close the window for glare? Okay, cool. So let's start off with just two-dimensional space. Oh, look at that. So good. So good. So I've got these two vectors, W, which has two components, and V, which has two components. And I'm going to define the inner product, or the dot product of these two. And I'm going to show you two notations that I'll probably slip up on and use. So we read this as W dot V, but I also might write that in this way with these brackets. This for me means the same thing, so I'm going to put that triple equality there. This means the same thing, dot product. I like this notation better. I think it's prettier. I think it's just kind of got everything contained in a little house. So the way we do this is we have these two vectors that each have two components. And look at all the parentheses and brackets floating around now. And we're going to multiply component-wise and add the results. So W1 times V1. So now this is scalar multiplication. This is the dot product. You just kind of got to keep the context in mind. This is just multiplying two real numbers together. W2 times V2. And then let's just do it in R3 because we're gonna treat this all as very general stuff. In R3, if I've got two vectors, W and V, W2, W3, comma, look, I'm already doing it. I'm already slipping up on the notation. So if this gets confusing, please help me out. Imagine there's a dot between those two. Same thing your book means. This is just W1, V1, W2 times V2, plus W3 times V3. I want to show you one other thing that just kind of came to mind. This is actually, we can think of this as just regular matrix multiplication. If I have a vector, if you know matrix multiplication, if I have the vector W1, W2, W3, and I multiply that by, so think of a matrix that's one row and 3 columns, and I multiply that by a matrix that's got 3 rows and 1 column. Think about how you multiply matrices together. It's essentially the dot product of the row times the column. So it's that times that. Well, it's the same thing as that right there. But you can think of it as matrix multiplication too. Is that making sense to any linear algebra folks in here? So when you do matrix multiplication, you got a big old matrix here, that'll come at some point. You just do row dotted with column, and you just look at all the possible ways to dot the row with the column. Everything cool so far? Yeah? Well, and you probably did some prep. I believe the pre-prep is now remotely correlated with the class at this point. Is that right? Yeah, it's a little past, can we read? And I think we got it. Okay, so let's look at some basic properties of this inner product, this dot product. And I'll try to stick to the book notation. So properties that we could prove using algebra, but we're not going to, because they'll take a while and I doubt that it'll give you any extra insight. So properties of the dot product, sorry. So first one is that if I take a vector W and I dot it with another vector V, I can do that in any order. Take a look at the definition. Could someone maybe tell us why that's true using some math lingo or just some properties of multiplication? So if I flip the position of these two, why would I get the same? Now let's think about it. If I put V here and W here, I would just be doing these things in a different order. What property is that? Good Lord. W2, V3, W3. So what allows me to say that those two things are the same?
Commutative?
Close, commutative. Yeah, that multiplication is commutative. You can do it in any order. And so this is kind of saying that dot product is commutative. It doesn't matter what order you do it in. Good thing, nice. This one I'm going to put, I'm not sure how our book does this, but I like to do this. The dot product is linear in each component. In fact, it's what's called a bilinear form. But what I mean more specifically is that if I've got alpha times W1 plus beta times V1, and I dot that with W2, let's put a U right here. So this is dot product. I've got a linear combination of vectors, and I don't know why I have ones here. Let's just get rid of those. We've got 3 letters, we're all good to go. That this is alpha times W1 dotted, W dotted with U, plus beta times V dotted with U. So there's kind of a distributive feeling. Kind of looks like distributive property of multiplication over addition, right? If these weren't vectors, which I should make them look like, you would totally believe that, because it's just the same thing with real numbers. That also works in this second component. So this is also equal to U dotted with this thing here. So it doesn't matter where I have this linear combination, I get the same thing. Could somebody maybe just, what's like a quick proof of that? Using stuff we've already seen. How would you tell, you're tutoring someone, and they're like, wait, why is this the same as this? And why are they both that?
Distribute the U to what's inside the front.
You can just, yeah, absolutely. And why can I do that in either? Yeah, you're absolutely right. Why can I do that from this right side or this left side and get the same answer? Commutative property. Yeah, beautiful. Hell yeah. Good stuff. Because this can just be written as this. Because I can switch the order in which I dot things, and then they're both equal to that. So, yeah. So you will probably use that one or two times. And here's kind of a cool one, that if I take a vector v and I dot it with itself, so I'm going to use both notations here. So this is v dot v, written both ways. Then this is the length of v squared. So that is the length of the vector squared. Let's take a look at y. Imagine this was a vector. I've got v1, v2, v3, and I'm dotting that with v1, v2, v3. Then it's component-wise multiplication, so it's that times that, plus that times that, plus that times that. And if I think about how I would compute the length of this vector, it's like super Pythagorean theorem. Sum of the squares of the components, square rooted. So this is the square root of those things squared. Just kind of undo the square root. Does that make sense, Kayla? I saw you like your head tilt there.
Yeah, no, we're good.
You're good, we're good. I'll never ask you to prove any of this stuff, but it's stuff we need to talk about. And honestly, the one that I really want you to focus on today is this one. So let's take a quick look. Let's just do some examples of some stuff, at least one particular example. So just a quick example of that last one, actually. If I wanted to find the length of the vector, were we using this for vectors? Maybe I won't use that for inner product then too, to like, kind of like a little overuse. So I won't be using this. I'll just say this. Sorry for getting too many different notations in the room. I hope that didn't mess anybody's brain up too much.
Said something.
What's that?
Until you said something.
Okay, now it doesn't make sense at all anymore. Oh man. So let's say I had this vector minus 1, 1 minus 1, 4, and I wanted its length. Well, what I could do is realize that its length squared is its dot product with itself. So what is that? That's 1 times 1 plus -1 times -1 plus 4 times 4. And that is squared. So 4 times 4. So what is that? It's 18. So the length squared is 18. So its length is just the square root of 18, which we could make simpler, but we don't care about that too much. All right. So dot product, inner product, is this weird operation that is like, why are we doing this? Why the heck would we do this? And so like somebody who's used it, why would you do this? Yeah.
In like coding, especially games, like if you ever need to find out how much like someone turns to the right or left in like a certain amount of time, I've used it a lot in that like specific case scenario.
That's awesome. Can you say a little more, because you got me, you had me at games.
So there was this player who I was making this one time, and I wanted to make it where you can't just like you're running straight at a certain speed and you turn really fast and you stay at that same speed. And so I would take like the dot product between your angle, if you like a fraction of a second ago, compared to how much you turned, and I would subtract your speed by that amount, so you can't like turn on a dime basically. You have to like slow down on turns.
That's awesome. And so the key word said there was angle, right? It's used to get angles. in vectors, between vectors. That's beautiful. Well, yeah, I kind of want to talk more about this, but we'll get going. I kind of want to know what kind of games you're coding up. That's cool. What language do you use?
I'm in Godot, so I use GScript and C++.
Cool. Very cool. Love it. So, the key use. There's two key uses. How about we say that? Two key uses of the dot product for us. So the first one, as Alan said, was to find angles between vectors. To find the angle theta between two vectors. And let's call them V and U. So I'm going to put the rule up, and then we'll talk about why we have the rule the way it is. So first off, draw a little picture. Now this picture is going to look like it's in 2D, but it actually goes to 3D or any D you want. So here's a 2D, but they could be floating in space, or they could be in 4-dimensional space somewhere that we can't picture, and then higher dimensions as well. This rule works no matter what. And the dot product extends to higher dimensions in the same way. Component-wise multiplication added up. So, we'll prove this in just a second, because it's a cool proof, but the cosine of that angle between them is their dot product divided by the product of their lengths. And another way to think about this is it's the dot product of the unit vectors in each of those directions. So put a dot here, like that. So you look at just like what are the core directions? What's the unit direction? What's the unit vector this way? What's the unit vector this way? Take the dot product. Literally, it's just the cosine of the angle between them. Weird. Seems weird until we look at the proof. And it still might seem a little weird because it's going to do some trig, and you're probably like, trig is just like a little vaporous for all of us at some point. Hopefully not too vaporous for me, right? I'm supposed to know something. So the legend goes. So that means that this theta is the arc cosine. So let's write arc. I like writing arc cosine. It's prettier than cosine inverse. People get weird ideas about that inverse also. U hat dot V hat U times V. So another thing I want to point out here, this is dot product. This is a scalar multiplication. So let's make a little note there that this is just scalar multiplication. This is the dot product, so context matters here. Let's actually just do an example. Find the angle betwixt, I haven't said that word in a while, so let's pop it out. Jackie's here today. Pull that up for Jackie. You're so welcome. Between U equals 1, oh, what was that weird ass angle I had? 1 minus 1, 4. And see, I even got the length for you already. V equals, okay, let me try to picture what's going on here, if I can even possibly do that. I think I can. And 0, 0, 1, negative 1. Can you find the angle between those two? You might need a calculator. I think we'll definitely need a calculator. Do you need a calculator, Jackie? Feel free to use your phone if you do. Just feel, everyone, if you don't have a calculator, use your phone. I appreciate that you never pull them out and watch some godforsaken video, but calculators are good. be some weird issues you encounter here. I hope so. That's what I want to talk about. What'd you say? You should be able to. I don't think you divided by. Let me see what you're doing here. Let's see. Wait. So it looks like copy that down. So what would you like to want? Something's a little wrong. Yeah. Okay. Cool. Awesome. Anybody else having trouble? You having any problems getting errors? Let me know. What'd you get, Kayla? Yeah, this sounds, I mean, I don't freaking know the answers, so sure. You getting 48-ish degrees? No?
Well, I don't have a calculator.
Oh, do you have a phone?
Nope, I do not have a phone.
Wow! You are a true mathematician.
No.
You have a sundial? Okay.
Figure something out.
I would give you mine. I appreciate it. Well, let me see. What did you get for the art coast? Certainly we have that.
Well, I have a cosine of
Yeah.
-5.
-5/6. Is that what we're getting for the?
Okay, it is -5/6.
The cosine of theta is -5/6.
Yes.
Cool. That's what I wanted the negative. That was all I cared
It's
about.
40 degrees. It's like, what's up?
I got 48 at first, but I messed up my dot product.
That's right.
I got like
I messed up my dot
46
product. I
degrees.
got 33 here.
You got what?
33, I think.
Oh, okay. We better. Maybe 48 is right. I will just do it together.
That's what I'm getting.
Oh, it's
That's
146. Yeah, it's my 146.
Because I was thinking it should be more than 90.
Yeah,
Oh,
I
I
got
got
146.
Yeah, what?
Oh, never mind.
Oh. Because I like in my mind I was trying to get him to be obtuse.
Unless I had one guess, but I didn't notice.
So I think it might be 90 plus that, Kayla, or.
Well, I messed up my dot product.
Wish I did
So.
Oh, okay, got it. Okay, this is cool. This is all good stuff. What direction is our character
I
headed?
had one too.
Dude, I had one of
Currently
these.
here.
Okay, cool. Take your
Going to the
time.
calculator.
Shattered everywhere.
I'll start working on it. What'd you get?
TI-85.
Oh, yeah.
Oh, yeah, right there.
One
That's
that
cool.
goes like, it literally has a solve function.
Yeah, it has like the mouse and shit.
Yeah.
Yeah. You can't usually do this in video.
No.
Standard.
Or like anything. Literally a computer. It's like a couple of steps Python.
Yeah,
exactly.
Just like code your own stuff.
You can do shit on here, but like the language groups, yeah, it was super bad.
It makes no sense.
That's just
square root.
I-
Oh, that worked out pretty good. That actually worked out shockingly well when you multiply that times that anyway. So let's see. So u dot v, length of u. If I say the word norm, I also mean length. Caught myself almost saying it. So let's see. So the dot product, I have a feeling it's -5, but it's only because I've seen everybody's answers. So it's 0 times, I'll just write it out. So it's 1 times 0 plus -1 times -1 plus 4 times 1. That looks like a 5. Nice. And then the length of u is root 18. Length of v is root 2.
You forgot, you messed it up.
What?
You messed it up.
How?
There's a the vector for v is 1 at the y. It's not -1.
Oh, thank you. Oh, these are switched. Thank you.
Yeah.
Cool. Oh, yeah.
That's
Shy.
Gotta get his attention.
No, it's good. That's good. So like that, and then that. Okay, gotcha.
Yeah,
Thank you. It's -5/6. Yes, thank you. Super important. I was about to make a horrific error. And then that's 5 over root 36, which is -5/6. Let's talk about cosine. because I wanted to talk about cosine. That's kind of part of this. That's why I made it negative. So we would have to riff about cosine and so what we know is that the cosine of the angle between these two things is negative 5/6. Now we're about to do arc cosine. Arc cosine is a weird thing, and as little as you feel you know about trig, you probably even know less about arc functions, arc trig functions. They just like the way it is. They're weird, and you don't spend much time on them. I feel like today we just moved past them because nobody wants to talk about them. So like you can freak out if we don't spend all that long. But cosine looks like this. So this is theta, and this is cos theta. A cosine graph looks like this. That's 1 period's worth. There's pi, 90 degrees. We don't use radians for graphs, or we don't use degrees. We use radians in general. There's pi over 2. There's pi over 2. Does that look legit? How high and low does that go? What's the amplitude?
-1.
1 and -1, absolutely. If we were in Calc 2, I'd make you memorize this and we'd have quizzes on it. Yes, yeah, just have it. All right, so this is 180, this is 90, this is 270, this is 360. When we want to think about the inverse cosine, so if I have inverse cosine of some x, so let's say this is the output x here, and then this is the output. Does the inverse to this function exist? Why not, Chris? I'm now starting to call you Chris, and then I like, yeah.
Don't
it's
worry,
okay.
either
Yeah.
one. Because it wouldn't pass the vertical line test. Like you wouldn't have a function, right?
Yeah, absolutely. Well, it does pass the vertical line test. It is a function because every vertical line.
Or like if you were to flip it.
The
like
flip
the
would,
inverse
yeah,
would-
absolutely, yeah. So he was saying that if I flip this over the y equals x line, well, here it'd be, the diagonal. Let's just call it that. If I flipped it over that, it wouldn't be a function because for every output value, there's actually multiple inputs that achieve it. So you don't know how to move backwards. If I said, what's the inverse of this? You'd be like, that or that? I don't know, or that, or that, or that, like this keeps on going. We want a unique answer. So what we do is we truncate this graph, and I guess, so you were totally right about the test. I was thinking about the horizontal line test, which ensures we're 1-to-1. We want one input for each output so that there's a unique relationship. So now what I do is I kind of just cut this piece out, and that represents our cosineville. That's cosine for us. Notice that it hits every possible output, and there's an input, exactly one input for every output. Now we flip that over the diagonal and it turns into this. And so this guy over here, this is -1, this is 1. That part, that vertical comes down like this, and then this is pi, and this is pi over 2. So this is 180, this is 90 degrees. So that's what an inverse cosine graph looks like. That's how you get there. Now, you don't have to repeat that. But we have to use it to make sense of what we're going to do when we get this thing out. When I say cosine inverse of -5/6, that -5/6 is right here. So what is the output? It's more than 90. It's right up there. So Kayla, why were you getting 48? Did you just have the wrong sign or something?
I just didn't see that it was 0 in one of the.
Okay, got it. Yeah, I mean, I didn't even copy it right, so fair enough, yeah. So when you do arc cosine, what do you get? What was the number you got?
146.
146 degree, and then point some garbage, right?
0.442.
What was that?
0.44 or 45, whatever you want.
Yeah, cool. Yeah, I like that. Thank you. 4 or 5 degrees. What is the radian equivalent?
It's like 2.5.
2.5. So let's just make sure that we can, I'm gonna put approximates here because these are not exact things. Let's just make sure we understand. Is everybody cool with radians and degrees? How do you convert from degrees to radians? Pi over 180. Yeah, so to convert this way, you put times pi over 180. To convert this way, you multiply by 180 over pi.
Radians.
Exactly. Because you want the degree thing on top if you want degrees out, and you want to get rid of, well,
Dimensionally accurate, that makes sense.
that's like how I do physics, right? It's just like units gotta cancel,
Yep,
right?
Yeah.
Don't know what I'm doing, but man, those units canceled right. Okay, so that's how we use that. So one thing to keep in mind here, and you can get a quick visual, if cosine of theta is positive, then the theta is acute. It's in the 0 to 90 degree range. Less 0 to 89.99 degrees. If cosine is negative, then you have an obtuse angle. Now you might say to yourself, well, wait a minute, how does that cover every possibility? But we're only gonna measure the smallest angle between two vectors. So like, here's two vectors floating in space. There is an angle out here, but we're gonna measure the smallest one. Any questions on that? Yeah, cool. Time, please. What time?
233.
43?
33.
33, awesome. A little scary. All right, so that's thing one you can do with vectors, with dot product. Thing two is a little weirder. So part two of the things I can do with dot product. The dot product, and this will be of key interest to us, allows us to project one vector onto the other. This is really what I was like, shit, we need to talk about this, because this is weird. And I never proved the dot product thing, just look in the book. That's fine, the formula cosine thing. It uses the law of cosines. I was all stoked to talk about it, but I think this is more important. I even I was practicing the proof when Jackie came to visit me, just to make sure I had it done. So the dot product allows us to project one vector v onto, that's a great math word, onto. I don't want to get into it, but man, that's a mathy word. If you've had logic and proof, you know what I'm talking about. Onto another vector u. It's a super overused word in math. I'm gonna kill myself. Get away. All right, so what do I do? I draw pictures. Here is v. Here is u. I'm gonna make them with different lengths. To project v onto u, I basically imagine that I'm gonna drop the plumb line from the tip of v to u. So I'm going to create that orthogonal triangle there. So from the tip of v onto u, what is the orthogonal drop?
90 degrees.
What's that?
What, is that what you're asking? Is it 90 degrees?
Oh no, yeah, it is 90 degrees. Yeah, thank you. Yeah, and this means 90 degrees. Yes. I know it sounded like a question, but I was kind of like, yeah. But you answered it beautifully. So I'm looking for this plumb distance here. That's like an old person word, isn't it? Do people still say plumb?
Nope.
Plumb.
Depends on what you do.
No, they don't. You're old. No, they definitely. It plums on what? Depends on what you do. Yeah. It's not like the fruit.
I've used it as a coder. That's,
Use it as a coder.
yeah,
What? How do you use it as a? What's the coding?
You just reroute stuff to go out there somewhere else.
Oh,
Take
sweet.
the data
Okay.
and dump it other.
Makes sense. Like some faster route or something. Or?
Oh, just like whatever you need to do it for.
Oh, okay.
So, sometimes faster, sometimes you just needed to go somewhere else.
Oh, got it. So it's not. So I was thinking of like the plumb line is you have this weight with a string and you hang it to see what's perfectly straight down.
Oh,
right? Yeah, so you get the plumb line for something. What's the vertical on it? So, what we want to find for the projection is this vector here. So this vector right here is the projection of V onto U. So let's talk about how we're going to do that first. Now, I am starting to think, what do we want to do? Let's actually pull out this length. So the first thing is, we're going to find this length. We're going to convert U to a unit vector, and then we're going to multiply that unit vector times this length here. So let me kind of show you the process here. Step one is find the length of the projection. That's going to be trig. Step two is, so let's call that L. Step two is multiply the unit vector in the direction of V by L. So the unit vector in the direction of V is just going to be V over its length. So we take V and divide it by its length, we got that unit vector. Does that make sense? Yeah.
Would it be U or V?
Thank you. On to you. Thank you. Yes, ma'am. Thank you. Good question. Yes. That is the thing I'm projecting onto. Awesome. Thank you. Yes. So let's actually draw out this picture here. I'm going to kind of rotate stuff so that it looks a little more straight up. So this is V here. This is a 90-degree angle. This is theta. How does this length L relate to this picture? This bottom one?
Find length with it.
Totally can. What kind of trig do I got to do? What do you see? Kayla's mouthing things.
I was saying like SOHCAHTOA.
SOHCAHTOA, hell yeah, I like it. Okay, absolutely. We're gonna SOHCAHTOA this thing. So let's take this little picture right here and SOHCAHTOA it. So if I have this triangle, here's the hypotenuse, here's the angle theta, here's the adjacent side to theta, and here is the opposite side. What is the sine of theta in relative to that picture?
Opposite.
Over H. That's the SO, right? And then, yes, I heard, yes. Alexander, you were saying it. Yes, sir. What's the cosine?
A over H.
That's the in SOHCAHTOA. And then tangent is what?
Opposite over adjacent.
Opposite over adjacent. SOHCAHTOA. Yeah? Vaguely familiar?
Yep.
Yeah, cool. Sometime in our lives, we have seen that. Cool. What is H in that picture? How do I find H?
Vector, the magnitude of V, yeah.
There we go, magnitude of V. So what we actually have is this is the magnitude of V, that length. I've got theta. So I know that the cosine, I'm gonna use cosine because I know about that dot product thing, right? That has cosine, that's how I can find that. The cosine of this theta is equal to the adjacent side over the length of the hypotenuse. And that is the length of V. Now I'm going to solve this for L. And I have my formula. So this means that L is equal to the length of V times the angle, the cosine of theta. It's like shocking. It's so shocking shit's going to fall off the table. How do I find the cosine of theta?
That arc cosine thing we did earlier.
That arc cosine thing we did earlier, right? We had that relationship. So this thing here, let's say, recall that the cosine of theta is u dot v over length of u, length of v. I'm going to use that formula. I'm gonna replace that here. So L, the length we want. See, I'm running out of space here. Get rid of this stuff. So L, the length, is equal to magnitude of V times this thing here, which is U dot V over length of U, length of V. Anything happen magically and awesomely? Cancel, we're gonna cancel. So L is U dot V, well, I keep putting the dot in the wrong place, over magnitude of U. And I'm gonna multiply that by this, the unit vector in the direction U. Wait, I feel, yeah, I think this is okay. So I gotta trust the math. I got a little scared there, but I think it's okay. So, therefore, this is the math symbol for therefore, those three little dots, by the way, that is therefore.
Yeah, it's a European thing.
What's that?
It's like a European, a lot of people in Europe use it.
Do they?
Yeah.
Is that
I
right?
just don't see it so much here in like American publications.
I'm a pretty continental kind of guy.
I use it all the time.
Yeah, absolutely. Nice. Okay, so therefore, and watch, I'm going to show some notation here. The projection, so I write proj of V onto U, that is the projection of V onto U, is equal to this length, U dot V, divided by U, times the unit vector in the direction of U, which is this. And now we have a formula, but we're gonna rewrite it one step. This is what you need to take out of this. I'm gonna put it in color. This is the formula you need right here, and here's the final version of it. It is equal to U dot V over magnitude of U squared times U. So notice what's going on here. This is a scale, this is a number, could be positive or negative. This is a number that will be positive, because we're not going to project onto nothing. And then I'm multiplying by a vector. So this right here is all a scalar, and this is a vector. Remember that you can write this U here, U squared, and you'll see this in the book, as U dot U. That was one of the first things we taught. All right, let's project some stuff. Sound good? Yes, Camila, you good? Was that question or?
No, I'm just trying to see that part.
Yeah, fair enough. All right, let's see, what were those two weird vectors we did the angle between?
Then you want another vector?
Yeah, I do, please, thank you. So let's say U was that
1, -1, 4.
Okay, so we're gonna project, we're gonna project this onto, and we'll do it both directions. And then what was the V, Alexander?
0, 1, -1.
Okay, cool, so let's find both. The projection of U onto V, and then let's also find the projection of V onto U. Just to practice that formula. So we're gonna use that formula right over there. Whew, that all went well. If anything was gonna go bad today, it was gonna be that. I made it.
Made it.
pay mind to what's being projected on it. Because the first one I wrote is literally the reverse of what I've written over there in terms of U and V, what roles they play. That's confusing. It's a pretty quick process. How do you use projections in your work? Probably.
I probably have, but I don't know if I remember though.
One of the things when I was a young budding programmer doing basic programming and stuff was hidden line removal. Boy, that stuff's weird. You know, when you have a 3D mesh or something, you're trying to hide what couldn't be seen.
Oh yeah.
I still don't even understand that.
Well, that's, yeah, I don't gotta do any of that
Yeah,
anymore.
that's crazy. That's crazy stuff. And let me know if anything's wrong. What?
Oh,
Decimals.
Is there, am I okay?
Yeah.
Woo!
Yeah.
Amen. All right.
What? Which one's which? That one. Yeah, okay.
Oh, really?
Yeah, that's fine.
Nice. Awesome.
Finished it. 2 seconds after you did it.
Outstanding. Outstanding.
Oh, yeah,
Doing
that's
it so
simple.
fast.
Oh, yeah, it's so fast.
Yeah. It was good last semester too. Like, I feel
Besides
like
the first time.
I feel like it's, yeah, I just feel like it's just like,
Yeah.
Yeah,
I'm
it's
getting
awesome.
used to what you want. I'm appealing to
School.
your, yep. I'm appealing to your teaching style. Like a good boy.
That's what I want. Obedience. There's nothing better. How we feel about this? Any questions, any troubles? Evan, you good on that too? Yeah. Zara, you doing good on that?
That's right.
Okay, cool, one last thing. Oh, I see, it's like 10 till? Just 10 till. I kinda cheated.
A little bit.
I left it a watch. So let's think back to this picture where I had this vector v and I was projecting it onto u, and I do this. So create this, I'm just gonna say plumb line, orthogonal drop from the tip of the one to the other. And now I've got this vector. So this thing here, this vector in black, oh boy. That vector in black is the projection of v onto u. Now, oftentimes when you are you're like doing physics, you want a frame of reference for where you're at. So not only do you want this component of a particular vector, but you want its vertical component as well. So the vertical component here, and we're gonna, can get very fancy, but not for us yet. So this thing right here, this is the orthogonal projection of V onto U. So imagining if this was a right angle here and I drew a stick or a vector straight up at 90 degrees away from U in the plane that V lives. And I'll get some pens out to make this make a little more sense. What is the height? What is the height of that vector relative to this vector? So let's get some notation. This is proj of U perp So that is U, that is U perp. That's how I'm gonna say it. That is a pretty legit way to say it. Onto V, of V. So the orthogonal projection, and orthogonal is just a great word, right? Orthogonal projection of V onto U. Let's notice something here. If I added this black vector plus that pink vector, what does the resulting vector look like?
That's V.
It's just V, yeah. So I'm saying, if I take this black vector here, plus the pink vector, how would I draw the sum? And it would be V. Does everybody see that? This plus that is V. So let's write this out. The projection of V onto U plus the projection of V onto U perp is V. And these are now decomposing that vector into orthogonal components. So if you were flying in space, or let's say you were like, you're here, here's a planet, you're orbiting that planet. And this would be maybe your horizontal vector. Your horizontal vector is going to be made with respect to the radius of a line stemming from the radius, taking the radius of the planet and extending it outward. This would be following the planet, right? If you're trying to orbit the planet, that's the direction you would be going. So let's say that I'm trying to get away from the planet and head in that direction, then I could break down the vector of travel into these two components. I could say I've got this component that is tangential to the planet, that is the orbit route, and then I've got this straight away from the planet vector. And so this is the orthogonal projection here. This is the projection onto my frame of reference.
Your orthogonal projections would be, you haven't drawn it in, right?
This guy here.
Oh,
That's what
okay.
yeah.
Gotcha.
Yeah,
Oh,
so
it's different, gotcha.
yeah, so if I'm orbiting a planet, my frame of reference might be this guy here. This is kind of my frame of reference, right? Straight up is with respect to the center of the planet, or you're just even on the surface of the planet, right? And you're trying to launch off the surface of the planet. This is the ground right there. And this is straight up in the sky. If you're standing on the earth there, your head's pointing up in that direction, and straight ahead is tangential to the surface. So you can think of things that way. So right now, if I just launch this pen this way, there's the projection down there, and then the orthogonal projection is straight up. That's all I got for you today. Oh, wait, one last, I want to rewrite this guy. Last one. How do you find this? Well, don't do anything fancy. Take the vector itself. This is what I wanted to say. The projection of V onto U perp is equal to the original vector, and you subtract off the projection. Does that make sense?
That's pretty straightforward.
That's pretty straightforward. So that's how you find your orthogonal projection.
Yeah.
Does this sound good? Cool. Let's call it a day. You've done well, my friends. What time is it now? Is it 3 o'clock?
It's 55:30.
What? 20 minutes? No, you can go. It's still. But we're gonna do work on Wednesday, and there is a pre-prep for Wednesday stuff, but it should be cake afterwards.
Should be cake.
Cake. Cheesecake cake. Plum cake. Yes. Yes, ma'am. So that is dot product from
No, it's
top.
okay.
Yeah.
Yeah.
But it will produce a first one as opposed to a vector. Does that make sense?
Right, that's what I'm saying.
Oh, and,
Let me hang out.